Over the last couple of weeks, I've been working on a new computer in Logisim. This one is based on a 16-bit platform, and I've got a little program running right here for you, which is just kind of a Fibonacci program. So there's a lot of devices that we have hooked up. One of them here is this teletype up here on the right, so we can display ASCII text to the user. We can take in keyboard inputs from this device right here. And there's a couple further down here that we'll discuss in a minute, but I'll just give you a little demo of this program. So we can type in an index into the Fibonacci sequence, and it will make a calculation for us. Now, if we pause the computer real quick, we can go look at what's going on here in the CPU. So in the brains of the computer, we have a bunch of registers where you're bringing in data through memory into these three general purpose registers. There's the A register, B register, and D register. A is an 8-bit and B is an 8-bit register, and they form a composite register called C. So if we want to load something into C and address the higher or lower byte within that 16 bits of C, we can just reference A or B. And then D is just a plain 16-bit register. We have a program counter, stack pointer, and index register, so we can do pointer arithmetic and move things on and off the CPU stack. And then down here we have a couple of internal registers. So things like setting flags to jump around in the program counter, and things to track what the current opcode is and the arguments that go along with that opcode. It's a pretty simple CPU. There's access to an ALU within it with a couple of 16-bit operations to do maths and logic. And within there, all of the handling is managed by this pipeline circuit here, which kind of just negotiates moving things between the opcode and arguments. If we go back up here, we can explore the programming language that we've set up for this CPU. So we moved over to the text editor to show you this programming language that we've set up to interface with this CPU. It's very similar to what you would see in C. It's a one-line based language, so every instruction is on one line. We're calling a couple of functions here, which exist in this graphics library here. So one is going to clear the screen on the video device in the CPU. We can set a color and send a fill rectangle command using these coordinates to the device. And then right here we just have an infinite while loop to hang the program. So if we save this file, we can go to our browser and run the page that is going to compile our code. It's a PHP compiler. We'll generate all of this machine code, and we just want to copy that, go to our CPU, and right click on the memory. Before that, it's good to hit Control R to just reset everything. But we'll edit the contents, and in this first memory address, we're going to paste in the machine code. And then to start the computer, all we have to do is press Control K. And it's going to start running the commands. So it's gone and cleared the screen. And in the color we selected, it's going to draw the rectangle on the video device with those coordinates. So on all these devices we have here, we have access to a lot of interesting functionality that we don't really want to do in code because it's going to be a lot slower. So here we have access to convert a number to a string. So any integer, we can make a string out of it. And same for the reverse. We can load in a string of characters and then pull out a 2-byte word out of it to get the number that string represents. We've done similar with floats, so if we can parse floats that the user types into the keyboard, and we can take floats that are in 16-byte and convert them to strings to display back. And same here, inside the CPU there's currently no way to do floating point arithmetic, but with this device here we can write a driver that lets us do all types of floating point maths using the integers. Now, a symptom of this is that the programming language has no access to parse any floating point integers, so any floating point that you have to put in, you'll have to convert into hex in the 16-bit format, and then it will get passed into here. Now, if we go to our video device, we can see a bunch of registers we have set here, so we can pass in commands and all types of information like the colors, any sort of coordinates. So this is the circuitry set up to draw rectangles on the screen, but we've also set up things to draw lines on the screen. And with that, I'll show you one of the programs we wrote to draw a triangle. So here's a program we've written to draw triangles on the screen. So first thing we're going to do is initialize the heap and allocate 16 bytes of memory. And we're going to save that memory address here into this chord input. So that's going to allow us to input coordinates into this string here. We're going to set the color for the screen, and then we're going to call this scanline function using that chord input value. So that's going to allow us to take in a string and save it to that memory address, and then it's going to return here in this return val. We're going to set this input length to the length of the string that was typed in. So we can call parse float, which is going to take that memory address to the string we want to parse, as well as the length of the string so it knows when to stop. And then for a return value from parse float, we're going to save into x1 the 16-bit value that we typed in. And so we're going to do that 6 times. So we have x1, y1, x2, y2, x3, and y3. We're going to take those 3 two-dimensional coordinates and send them to the draw float triangle, and then hang the program. So if we save this and go to our compiler, refresh the page, and copy the machine code that it generates, we'll go back to our CPU, hit Control-R to refresh, right-click the memory, paste it in, and then start the clock to start the program. Now over here, once it's initialized, we can start typing in coordinates for our triangle. So if we type in 0.2 and 0.2, that's going to set up a first coordinate right here in the top left of the screen. That's 0.2 of the 256 pixels that we have available in this video device. And so we can set up a second coordinate, so 0.6 and 0.8. And then we'll do 0.3 and 0.7. Now that we've put in all 6 inputs, it's going to take that and draw the triangle that we just inputted. Now I wanted to take this further and be able to rasterize a whole triangle within this video device. So on top of the line rasterizer, I took that and developed a 3D triangle rasterization circuit. So this works similarly to how a real GPU in real life would be set. As an input, you have a 3-dimensional coordinate. It's going to take 3 3-dimensional coordinates, x1, y1, and z. And then for each of those, it's going to take in a color. And it's going to project those coordinates based on the z value to our 2-dimensional screen. And then it's going to interpolate between those 2D coordinates and the colors that we pass along. So I'll show you what that would look like in code. So here we're defining 2 triangles in the global variable space, and it is a struct of 16-bit floating point integers that we've set up. So here we have just a buffer byte, or buffer of 2 bytes here, and then we have our x coordinate, y coordinate, and z coordinate, and then the red, green, and blue value. These are represented as a value between 0 and 1. And then same for our second coordinate, and our third coordinate. So there are 2 bytes per coordinate, which means 6 bytes per point in 3D space, and then another 6 bytes for the color, so that's 12 bytes per point. Now here we're going to call our clear screen and this fill triangle function on both of these triangle structs that we have set up, and that's going to draw both of them in 3D space. So if we go to our compiler, load the program, we can see here it's going to start drawing our first triangle. So we have a blue corner, a red corner, and down here on the right is a green corner. And then we have a second triangle that's going to intersect with this first triangle. And since we're implementing a Z buffer, it's going to show you which one is in front, and you'll see them intersect right here. Now they're both complete. You can see that this triangle here is intersecting with this one in 3D space. Now to take that even further, I wanted to try and draw a cube on the screen. So what we've done here is set up a series of 8 triangles that are all encoded in the structs up here. I'm going to call fill triangle 8 times. Reset the CPU with Control R, paste in the machine code, and hit Control K to start. And I'll just zoom in here on the video device so we can see this run. Now, if you want to be able to use this CPU for yourself, you can go to the GitHub repository, and here we have all of the files that you need to run this for yourself. So inside of app, you'll find the v5.circ, which is the circuit that we're loading here in Logisim Evolution. And if we want to compile code, we can just clone this repository. And say we've just cloned it, we can run this command, docker compose up-d-build, and that will set up a Docker container to run the program and build the compiler. So that is going to look inside of this app directory here, and it's going to look at this main.dinc file, which is the entry point for our program. Inside of there, we're doing a bunch of includes to other files. So this standard lib has functions to do memory allocation. Standard IO can bring in and remove text from the keyboard and to the teletype. The string will do a bunch of string operations. We can do some math operations, hashing, a linked list. We have this triangle to draw 3D triangles. We have a graphics library to draw lines and rectangles. A float operation to work with floating point numbers. And then here in this bin slash, we have programs that we've written, like a calculator, a Fibonacci program, and a shell. So you can go in and explore all that for examples on how to use the programming language. And to compile, here in this app directory, we want to open up this assembler.php file. It says assembler, but it's really a compiler. And if we go to port 8080 of localhost, that'll go to the Docker container and load that assembler.php file and generate the machine code for us. which we can then paste into here. If you don't want to do any of that, you can just go to the GitHub repo, and then in this binaries directory, we have a couple of programs that I've displayed in the video here. So you can just click on one of these, copy the machine code, and paste it just like before. If you got any more interest in this kind of program and ideas for how I can make it different, please leave a comment and a like. Thank you.